Welcome back, everyone. Lecture 15 brings us to the chain rule. In my opinion, I think this is where the material starts to get pretty fun. But for what's fun for me might not be fun for you. I like it because the derivatives start to get very messy, and they start to look kind of complicated. Let me give you an example of a function that you might want to use the chain rule to find the derivative of. So let's consider f of x equals, and it's going to be sine of x squared. So this isn't something like sine of x times x squared. This is a function composition. And at this time, we don't really have a rule to deal with something like this, where I have a function plugged into another one. So let me write that down. So we do not have a derivative rule for this function. At present, we're about to, but we do not have a derivative rule for this function. Using function composition, let's do the following. So we're going to say capital F of x is equal to f of g of x, where you could think of g of x as my inside function, the one that's getting plugged in. So I'll say f of x is sine of x. That's my outside function. So I'll even write that. I'll be frequently referring to these as outside and inside. And then g of x is x squared. It's kind of the inside function. So if you look at this, f of g of x is f of g of x is x squared. And if I plug x squared into f, I really do get the sine x squared that I started with. So f is equal to some kind of composition of functions. And remember, this is just f of g of x. That was our review material. So how do I deal with something like this? Well, here's the rule. The derivative of f of g of x. So where I have one function being plugged into the other is the derivative of the outside function. I'm going to plug in the original inside function, and then I'm going to multiply by the derivative of the inside function. So it looks kind of messy, but we'll do many examples to practice this. So let's go ahead and try the example we have here. So we're going to return to f of x equals sine of x squared. Now my inner and outer functions are f of x and g of x. F of x is sine of x. For this derivative rule, it's helpful to have the derivative of that. So the derivative of sine of x, based on our last lecture video, is cosine of x. The derivative of the inside function, which is x squared, that's going to be 2x based on the power rule. OK, so let's go ahead and plug everything in now that we have all four of these. So f prime of x, so the derivative of this function, I need the derivative of f. So this is going to be cosine. It's going to be cosine evaluated, though, at g of x. So g of x is x squared, times, and then the derivative of the inner function here. So that's going to be 2x. So this is my derivative of sine of x squared. OK, so that's not too bad. Let's look at a different example. Let's look at, we're going to say capital F of x is equal to the square root of x cubed minus 3x squared. This is equal to x cubed minus 3x squared to the 1/2 power. I always like rewriting my root functions like that first before I begin. So the question is, what's my inner, what's my outer function? Well, The one that's on the very outside of everything, the outer function here, is the square root function. So the square root function is actually my outer function this time. My inner function, I hope I can fit this here, the inner function is going to be what's plugged inside here. So this is the inner function. This is x cubed minus 3x squared. It looks like I fit that there. I'm going to scoot this over. Then the derivative of the outside function is 1 over 2 x to the 1/2. So I got that by doing the power rule. You bring the 1/2 down, subtract 1 from the power, it's now a negative 1/2. G prime of x, this is just a polynomial, so I'll do the power rule a couple times. I'll get 3x squared minus 6x. OK, so now that I've sat there, I wrote out what the inner and outer functions are and their derivatives. I'm going to go ahead and do this the same way as before. So this is equal to f prime of g of x times g prime of x. Let's fill it in. So what I need to do is I need to write what f prime is, but I'm going to plug in g of x into it. So this is going to be 1 over 2 times x cubed minus 3x squared to the 1/2 power. So I've plugged in g of x into my f prime. And now I'm going to multiply by g prime, which is 3x squared minus 6x. If I wanted, I could just write this as 3x squared minus 6x all over 2. I could even turn this back into a radical if I wanted to. Radical x cubed minus 3x squared. OK, so if you want to do it this way, what I do is I identify what the inner and outer functions are. I list them. And then I go back and I fill in everything I need. All right, let's continue. So let's do another example. This time my example is going to involve e. So it'll be e, but instead of just e to the x this time, it's e to the cosine x plus 2. OK, so my inner function is this. You could think of this as g of x. What's my outer function, the thing on the outside? Well, f of x is e to the x. And once you plug in g of x, you get this function here. So I think this will be the last time I write this all out. But you can keep doing that if you want until you get comfortable with this idea. My inner function here is cosine of x plus 2. That's what's getting plugged into e to the x. The derivative of e to the x, which is very nice. This is just e to the x. And the derivative of cosine x plus 2 is negative sine x. And that's it, because the derivative of 2 is just 0. All right, so I'm going to go ahead and plug everything in now. So y prime is the derivative of f at g times g prime of x. It's me just writing the chain rule formula. F prime is this e to the x function. So it's e to the, and instead of x, I'm going to plug in g of x, which is cosine of x plus 2, and then times g of x, which is minus sine of x. OK, so hopefully you kind of see the routine, like what we're doing. You can use something like this to help you along the way. Let me do one more example. So we're going to take the derivative of something a little more complicated this time. It's going to be e to the x squared times cosine of x squared plus 1. So in this case, we have a lot to deal with. And we need to really step back and think about what the overall rule is that we're going to be trying to accomplish. So what I see is I have this function times this function. So overall, this is a product rule. And then as we're doing the product rule, you might need to bring up other rules and take care of those along the way. So the product rule says what? Well, you leave the first one alone. So I'm going to leave e to the x squared alone, if this is my f and this is my g for the product rule. So I should probably even write that we're doing product rule overall, but you're going to see other rules happening. I'll rewrite f. I need the derivative of g, but that's a chain rule because I have cosine of not just x, but something more complicated. So how do I do the chain rule here? I'm going to not write it out like this. The derivative of the outside, cosine, is negative sine. Here's the inside, so I'm going to plug that in. And then times, what's the derivative of the inner function, g of x? That's going to be 2x. Plus, so don't lose sight of what we're doing. All I've done is I've taken f, I've rewritten it, and then this is the derivative of g using the chain rule. Now I do plus, and I switch the order for the product rule. So now I'm going to need to find the derivative of e to the x squared. Well, that is another chain rule. So what I'm going to do is I'm going to look at the outer function. What's the derivative of the outer function of e to the x? It's just e to the x. So I have e. I'm going to plug in my inner function here, and then multiply by the derivative of the inner, which is 2x. What's the last thing I haven't done for the product rule yet? I've taken the derivative of this. I have not taken the derivative of this. Oh, no, sorry. I have taken the derivative of both of them. I haven't rewritten this one yet. So this is times cosine x squared plus 1. OK? So this is f derivative of g plus derivative of f, g. And we can probably make this look a little better now. So all of them have a 2x and an e to the x squared in common. So you can see that in both terms. And what I'm left with here is cosine of x squared plus 1 minus sine of x squared plus 1. And that at least looks a little better than what we started with. OK, so you can kind of start to see how these could get difficult very quickly. There's a lot of things to keep track of. And chain rule is just something you're always going to have to keep in the back of your mind now as you're doing derivative problems. The idea is if you're dealing with a function that's just more complicated than what it normally is, so for example, the standard sine function looks like this, but if I have sine of anything more complicated, then that's when you have to use the chain rule, when you're looking at not just the standard parent function. OK, so I'll be back in just a second, and we'll do more examples. So see you soon. So the next thing I'd like to talk about is the fact that we could have nested chain rules. And what this means is you could require more than one use of the application of chain rule in a problem. So here's my first example. Let's say our function was y equals sine of tangent of x squared minus 1. So we kind of have this layering going on where I plugged x squared plus 1 into tangent, and then I plugged that whole blob into sine. So this has kind of got a flavor like this, where it's f of g of h of x. I've just got like another layer of my composition. But we can do many application of chain rule to take care of this as well. So let's start with the derivative now. The derivative of the very outside, so I'm going to start outside here. The very outside here of sine is cosine. And then I'm going to evaluate it at its inner. So this is going to be the inner if I have just this as the outside and this is what's left inside. This is going to be cosine of tangent of x squared minus 1 times the derivative of the inside. So that's the standard chain rule, derivative of this. However, you would do one application like that, but you'd see that you're not done because this is another chain rule, because still I have this function is inside tangent. So I'm going to need another chain rule to take care of this. Thankfully, we're done with this part, so you just keep carrying this down as we go. So let's keep going. I'm going to carry this part down that I've taken care of already. The derivative of this is another chain rule. It looks more like the ones we just did. The derivative of the outside function is secant squared. We learned that in the last video. So this is secant squared. evaluate it at the inner function, which is x squared minus 1. Then we do the derivative of the inner function for this one, which is the derivative of x squared minus 1. OK, we're almost there. This doesn't require the chain rule anymore, right? This is just a power rule and a derivative of a constant. So my final answer will just be cosine of tangent of x squared minus 1 times secant squared x squared minus 1. And the derivative of this is just times 2x. So that just required 2 applications of the chain rule. But the way to handle it is just to start on the outside, work your way in. If you're methodical and just keep track of what the derivative of the remaining piece is, like I did, then you can kind of ignore the stuff you've already taken care of. You can push it out of your mind. So that's how you can handle this. I'm going to rewrite this next example using my standard trick where I raise it to the 1/2 power. But something else I'm going to do that I think I'm going to suggest that you do this too. If you have a trig function that's to a power other than 1, you might want to rewrite this like this. So tangent squared is tangent squared, like that. So tangent to the first power all squared. These mean the same thing. Let me put a note for you down here. So tangent squared of x is the same thing as tangent x squared, like that. I keep accidentally doing that. OK. So it's more useful for chain rule, in my opinion, to have it like this. So you can see the inner function is tangent, and the outer function would be x squared, right? You have something squared, that's my outer function. My inner is tangent. So that's why I suggest writing it like that. Anyway, back over here. This is tangent squared. This is e to the 2x. So now I've rewritten this, so this whole thing is to the 1/2 power. Let's do the chain rule. So I should call this something, shouldn't I? So this example, this will be y. OK, so this function is called y prime. The derivative of my outer function is, it's the root function, right? That's on the very outside. So let's take this 1/2 power. Let's bring it to the front by doing the power rule, 1/2. I'm going to rewrite my inner function here, which is tangent x squared plus e to the 2x. And this is going to be now to the negative 1/2 power, because I applied the power rule for the outside function. So I brought this power all the way in front. I rewrote the inside, just plugged it in. And now I'm going to do the derivative of the inside, which is tangent x squared plus e to the 2x. So I'm looking for this derivative right here now. I've already taken care of this part. OK, let me go ahead and rewrite this. This is going to be 1/2 tangent x squared plus e to the 2x to the negative 1/2. The derivative of this now. So this and this both require chain rules separately. So derivative of tangent is going to be secant squared. That's going to be involved. But my outer function is a squared function. So for this, I'm going to bring the 2 forward, rewrite tangent x. It's my inner function. 2 lowers down to 1 because of the power rule. I'm going to multiply by the derivative of tangent. That's my inner function. Plus, now I'm working on this one. The outside function here is e. So I'm going to have e to the 2x. I'm just going to go ahead and plug in my inner function. And this is times the derivative of my inner function, which is 2x. All right, I'm almost there. So now I have y prime equals 1/2 tangent of x squared plus e to the 2x to the negative 1/2. I think I have one too many parentheses here. Let me just go like that. OK. Here I have 2 tangent. It's to the first power. I don't need to write that. Derivative of tangent is secant squared plus e to the 2x. And the derivative of 2x is just 2. So I'll put that up front here. OK, and if I wanted to write that a little nicer, this whole thing right here is to the negative 1/2 power. So I could bring that to the denominator. And this looks like 2 radical, and I have tangent squared x plus e to the 2x. And then this piece right here remains in the numerator, 2 tangent x secant squared x plus 2e to the 2x. You could also notice that every single term has a 2, so I don't even really need the 2 there either. I can just leave it like that. OK, so again, it is just doing things in stages and keeping track of what you've already done. And if you've done something, just keep it to the left. I'm sure here that I have lots of parentheses that I probably should not have, like this one I'm kind of noticing, and also this one. Just trying to keep my syntax in order here. I think that's good for that now. This is also kind of iffy. I don't need this one. OK, anyway, I could sit here and just pick up my syntax all day. But let's look at this last example that I have written here. So it says, suppose h of x is f of g of x plus 7x squared. And our goal is going to be to calculate h prime of 1. And they give us a bunch of different pieces of information here. We may not necessarily use all of them. Sometimes in questions like this, they give you a surplus of information just to trick you and have you grab the wrong pieces. So we're just going to look at the ones we need. But here's everything and more that we do need. So if I'm looking for the derivative of this function, I'm going to need the chain rule. So h prime of x is, the derivative of a composition of functions like this is just the chain rule. So the derivative of this piece is f prime at g of x times g prime of x. So this is the derivative of this piece, plus, and then I just do the derivative of this. So that's going to be, if I bring the 2 down, that's plus 14x. OK? So now I would like the derivative of h at 1. So everywhere you see an x, we're going to go ahead and plug in a 1. So I saw 3 different places where I could plug in an x, or 1 for x. So I went ahead and I took care of that. So this is where we start using our information, and we realize we have too many things to deal with. Not to deal with, but too many things for spots here. I'm only going to need to plug in a couple things. OK, so let's take a look at that. So this is going to be f prime of g of 1. That's 8. G prime of 1, I have to search for that. That's 10. So times 10 plus 14. Now I need f prime of 8, because that's what happened when I plugged in 1 here. So f prime of 8 is 2 times 10 plus 14. So this is going to be 20 plus 14 is 34. What did I not use? I don't think I used this. I don't think I used this. The only ones I used were g prime of 1, g of 1, and f prime of 8. OK. So this is 34. So even if you have an abstract function like this where it doesn't really tell you the name of everything, you should still be able to compute derivatives using the chain rule or any of those other rules we've learned so far. OK, I think that about wraps it up for this video. I will see you next time, where I believe we're going to be talking about implicit differentiation. So I'll see you then. Thanks for watching.